Physics, electric currents and magnetic fields. So for this, for the figure below, we have basically a wire, and there's a current flowing through this, and our question for this is, at some distance away from this wire, how large must the current be to produce a magnetic field of 2 times 10 to the negative 4th Teslas at a distance of 2 centimeters from the wire as shown? So what is the direction of the field at this point? So 2 questions here. First, let's go ahead and list out our knowns, what's happening in this. So B is what is known as the magnetic field strength. It's measured in Teslas, as you can see here, and it is 2 times 10 to the negative 4th Teslas is our field strength. Distance that we're dealing with is 0.02 meters, or 2 centimeters. And then our mu naught, which is I believe it's a permeability constant for magnetic fields, is 4 pi times 10 to the negative 7th Tesla meters per ampere. Alright, what we are looking for the current and the field direction. So for this, we know one very important equation, and that's for calculating the strength of the magnetic field. We, however, do not need to calculate the strength of the magnetic field. We know what it is. What we are looking for is how large the source that's creating this field is. In other words, how big is the current, how large is it? So what we're going to do is we're going to go ahead and solve the this force equation, this B equals mu naught I divided by 2 pi d for I. And when we do that, we get I is equal to B times 2 times pi times d divided by mu naught. Then we can go ahead and plug in numbers and solve for I. So when we do that, we get I is equal to your B, which is 2.0 times 10 to the negative 4th Teslas times 2 times pi times 0.02 meters. And then we divide that all by mu naught, which is our standard 4 pi times 10 to the negative 7th Tesla meters per ampere. Okay, and then when we plug in numbers for all that, we get I equals 20 amps. So, a fairly large current. Okay, and then for finding the direction of the field, this is something somewhat more interesting, and it requires some interaction and some visualization. Specifically, one of the easiest ways to find magnetic fields and their directions is by using what is called the right-hand rule. So the right-hand rule is kind of interesting. The first thing you need to do is basically you need to have your palm flat and your thumb extended, and then point your thumb in the direction of the current, keeping the rest of your palm flat. And then once you've done that, you can fold your fingers into your palm, and when you do that, basically going from knuckle to fingertip will be the direction of the field lines. And this direction is very helpful, or this direction is helpful for finding whether or not the field is going into or out of the page at this point. So as was seen up in the figure above, the point is above the wire, and the wire with the current going to the right, when you basically do the right-hand rule and determine which way the field lines are going, you see that the field lines for this would be coming out of the board or out of the page for this. And so we know that when you do this, the current comes. We know that the B, basically your magnetic field, is out of the board or out of the page. Depending on where you're working, or in this case, computer screen. So, and then just a good way to visualize it is if you have a wire and the current is coming, say, straight out of the wire in terms of the direction you're looking at it, the field will be going counterclockwise or anti-clockwise, and that's one way to remember it. But probably the easiest way to do it is just to use the right hand rule. Don't use your left hand; it won't work. Just use your right hand.